Good afternoon. It's my pleasure this afternoon to introduce the plenary speakers for this afternoon, Dr. Terry Root and Dr. Schneider, both who have been very active in conducting research on climate change and its impact on the environment and species in particular. They were both honored recently by the National Wildlife Federation for the quality of their research and their effectiveness at the Science Policy Interface. Dr. Root is a senior fellow at the Center for Environmental Science and Policy and a professor by courtesy in biological sciences at Stanford University. She is a Pew Scholar in Conservation and an Aldo Leopold Leadership Fellow. She was the lead author for Wildlife for the 2000 Intergovernmental Panel on Climate Change. Her work has focused on past and probable future ecological consequences of global warming, and she's been a pioneer in modeling predicted distributions of species in response to habitat variables. Dr. Schneider from Stanford University is a professor of biological sciences, a senior fellow and co-director of the Center for Environmental Science and Policy, co-director of the new interdisciplinary graduate program in Environment and Resources at Stanford, and a professor by courtesy in the Department of Civil and Environmental Engineering. And he tells me that this alphabet soup of affiliations is because Stanford is organized by disciplinary departments rather than problem departments. He works on climate change, the science, impacts, and policy aspects of climate change, and he is active, as was Terry, in the Intergovernmental Panel on Climate Change, which he calls his night job, and he's very involved in the overall debate over global warming, has advised people at the highest levels in the previous administration, and is a regular participant in congressional hearings. Please join me in welcoming Dr. Schneider, to be followed by Dr. Terry Root.
Thank you very much for that, Mike. Buzz Thompson noted that we started late, 1:30. Okay, well, the reason I mention that is that we have an awful lot to cover, and we want to make certain we have some time for question and answers. So I'll get right to it. Let me start before I do that by saying I had this page of notes after the Thursday session and the governor's talk, and I can't resist but do it because I teach my students that you're supposed to say first, what are you going to tell people? So I'll tell you what I want to tell you, but even though I have a job that's only going to partly tell you that. First, the issue came up many times about volunteerism. And just briefly, I enjoyed immensely the governor's fun stories about his motorcycling around with the two cops on the motorcycle. And then he noted the dangerous drivers swerving around them and cutting them off until they saw the cops and they pulled over and behaved. And I would remind you that's the message, is that without enforcement, people's behavior is rather different. In fact, so I won't be partisan and just say that the Bush administration is the climate problem, although they are. But the previous one also, who signed on to, in fact, it was Bush Sr. who signed the United Nations Framework Convention on Climate Change, which committed us to work toward cuts in emissions. Well, we've had an interesting history since then. So both Clinton and now Bush called for voluntary policies to curb emissions. And they both had the same result, no result. And that's because it's very difficult to make things work without rules. The U.S. is a little more than 10% more emissions than it was a decade ago, and a good fraction of the reason for that is because the sport utility vehicles are not under CAFE. So again, without incentives, and people have said that over and over again, and I'm making the point here in the case of climate because it's a parallel point to what I've heard many times, and I thoroughly agree that incentives are essential. In fact, my next set of notes says, yes, incentives work, but first we need rules to push them and real funds to implement them. And we've heard that from other people. That is equally true in the case of climate change. Carbon emissions are going to go up unless market incentives or quantity limits are not only put in there, but they're enforced. And that's what leads to those behaviors. Then a free market is very, very good at efficiently allocating how to do that, but the rules have to be set usually at a different level. Finally, I didn't hear anyone talk about this in the context of the Endangered Species Act, and I'm not going to have time since I'm going to set up the science of the climate in a minute when I get to PowerPoints, but the question, overall question for policy that drives it is, well, this is just going to cost a lot. And you will hear all the time in the climate debate opponents of rules telling you the, quote, prohibitive costs of tens of billions or even trillions of dollars. Now, there are a whole lots of unfavorable assumptions in those numbers, but let's just for the minute buy that those numbers are correct. If you take a look, there's almost always omitted a certain perspective. Now, let me read my numbers. The Kyoto Protocol, for example, which is considered by this administration and many in industry as unacceptably expensive, would cost tens of billions of dollars. If you take a look and do a sober, detached economic analysis, you know, the kind Jeff Hill's taught me to do for the last 25 years, and I shouldn't give Jeff the blame for that, but what you find is that something like Kyoto, given the growth rate in the economy projected in all standard neoclassical economic growth models, basically suggests that with Kyoto, the average American is 25% richer in April of 2012, that's right. Without Kyoto, they're 25% richer in January of 2012. And in fact, if you run the numbers for the whole century, again, using neoclassical economic growth models, which assume population increase, increased productivity of labor, you get something like a 2% per year growth rate. So when you look, again, at pessimistic assumptions about costs in the context of this overall global issue, you take the $30 trillion economy, what's the right number now, Jeff? I don't know. That order? Okay, and you have a 2% growth rate, so that means in 100 years it's a factor of 8 bigger, a $240 trillion economy. And then you start weighing the $1 trillion or the few $1 trillion that the opponents say that this is going to cost to fix the problem through mitigation, through shutting down coal plants and a whole range of other expenses. And again, just believing that, when you take a look at it, what you end up with pessimistic assumptions is that you could essentially avoid the problem that Terry and I are going to spend, most of the next 40 minutes telling you about at something like 2% GDP loss in 100 years. Well, that's an incredibly large number. That's trillions of dollars. But when you look at that as the relative fraction of the growth of the economy because of the growth rates, it means that the world is, the average person, this is assuming population growth, is 500% richer in 2102 relative to 2100. And therefore, there is no macroeconomic, economically devastating event in trying to solve the climate problem. That is simply nonsense. That is misrepresentation. But there's severe local dislocation. It's not going to be good for people who make SUVs. It's difficult for coal miners. So the question that we have to deal with, and I think there's a lot of parallels in the ESA, is first, is there a significant macroeconomic cost? And I don't know that, and I want somebody to answer it, but I suspect the answer is no. It's well below the growth rate in the GDP. The question is dealing fairly with the distribution of impacts and setting up those incentives and setting up the side payments and the transfers so that we can get people on board. And I think that is legitimate, both in climate and in ESA. And that's why I wanted to make those prefatory remarks before I do the job I have, which is to talk about the background science, climate change. Oh, okay. So, which one do I hit?
Either one. You get the carriage return a couple of times, and that'll get you out of there.
Okay.
One more time. There you go.
All right. So now I'll just go and find mine. Oh, I was going to find it on the file. There it is. Usually they say 4 things. Okay. Where's the wine glass? I just want you to know the way my brain works. Okay. I always have one of these because a lot of times it doesn't, and it's nice that it does now. Only a little bit of glitch. I'm always entertained when these things fail because it gives me a chance for one of my favorite, extemporaneous pieces of humor, which is that there are people who think we can coordinate 10,000 lasers in space under attack, too. They've obviously never used PowerPoint. Okay. How am I doing, Shahid? Is it all right? Okay. Somebody said we're supposed to do this. Okay, let's get, sorry, we got to get serious. At dinner the other night, I think it was Mark, who had been, in my view, duped by some nonsense about how the sun did it. And I figure that's a pretty smart guy, and he clearly is, an environmentally oriented type, so therefore, clearly this must have been compelling. It couldn't have been an ideological bias. We know you don't have any of those, Mark. Certainly not in that direction. Okay, so what I wanted to show you is why it is that the vast bulk of the mainstream climatological community makes the bold assertion that there's a discernible impact of human activities on climate, and in fact that the recent several decades are almost certainly warmer than we've seen in the last 1 to 2,000 years, and most likely a good fraction of it, more than half, is due to us. Okay, I'll do it fast. So, whoops. There we go. Well, I'm going to use the machine I know. All right, so let's start over here at this one. Yeah, well, I told you lasers don't work very well. You're supposed to press both buttons at once. There we go. Yeah, I was. Okay. What we're looking at in red is the thermometer record for the last 150 years or so, and that's the global warming. It doesn't matter what Professor Limbaugh tells you. The world is warming. In fact, the only thing of his you should trust is when he gives you advice about prescription drugs. But this thing up here, yeah, some of you got that. All right, up here is the most unusual period. You can't distinguish most of what's going on from natural fluctuations that you get in the last 30 years or so. Now, what is this? So this is instrumental, that's red. What's this gray thing, which may be hard to see? The gray thing is what a computer model tells you the temperature would look like due to a combination of factors: internal natural variability, unpredictable randomness in the model, and the model driven by natural forcing only. Natural forcing means volcanic eruptions throw dust in the stratosphere, cool you down. It also means the sun that we were talking about, Mark. And when you account for both of them, you get a record that looks like that. Remember, if you picked any other time block, it would have the same spectral characteristics, but it would be different in its phase. And you can see there are some periods that agree this is slightly correlated with the record, but not very much. Now you go to anthropogenic forcing, right? That's us. And this is primarily, we debate exactly what that is, but this is primarily greenhouse gases, the 30% more CO2 and the 150% more methane and a number of other things. And we can translate those into a couple of watts of energy trapped over every square meter of the Earth. That's like a Christmas tree bulb over every square meter, but in the infrared. And then you reflect some energy away because sulfate aerosols produced from burning high sulfur coal and oil cools, and they do that heterogeneously. In any case, if you do that, the gray, as you see, is a better fit to the red, but still not perfect. Now, what happens if you look at natural plus anthropogenic? You get an even better fit. Now, does this prove things? No. This is circumstantial evidence. But the probability, the subjective probability, because that's what it always is, because there are always factors you can't control, that we're in the game goes up every time you play games like this. And I'm not going to tell you, because we don't have time, that we look at many other fingerprints. We look at stratospheric cooling and surface warming and high latitudes warming more than low latitudes and continents more than oceans. Every one of those is a fingerprint of anthropogenic change. Every one of those have happened. Every one of those is assailable circumstantial evidence by itself, and is assailed in the media debate by people who don't like it. In fact, it's assailed by those of us who write it up. The point is, when you look at them all together and they all line up, what's the probability they're all lining up by chance? Not very high, and that's why you will find the community over and over and over again, while cautiously saying each element is problematic, the collection looks pretty much like something real is going on. So that's the backdrop as to why you should now listen to the next 15 minutes, where we're going to talk not about the past, but about the future. Okay, so how do we talk about the future? I always like to show this one when I'm talking about the incredible, brilliance of this debate in the media. But Nostradamus over here, he makes me jealous, because you can't forecast the future without a crystal ball, and unlike ours, his is clear. And our crystal balls are basically mathematical models, and what they do is they codify our best understanding of the multiple interacting subsystems that we think determines the future. So we have a submodel for the atmosphere, for the oceans, for the forests, for ecosystems in general. And that then gives us our Earth system model. And we tune those to, as best we can, past and present observations codified by understanding where physical laws make sense, and go through a very rigorous process to try to test it. But in the end, there is no empirical test of the future except waiting until it happens. So everything I'm going to say about the future will involve confidence judgments made on subjective grounds. And the primary subjective ground is whether or not the quote-unquote objective information we use to derive the submodels will still be valid far in the future when conditions are different. And that is a judgment. And that's where the science comes out, not in the fact that we could people will say, well, you can't produce objective statistics about these models, so therefore we shouldn't believe them. Well, what can we produce objective statistics about in the future? Nothing. So therefore we have nonetheless expert judgments based on objective statistics, but they all will decrease their accuracy over time. So those are our cloudy crystal balls. But not only do we have those Earth system models, but we also have to have models of how the world is going to work. So this is one of my favorite little cartoons. We're not certain why they disappeared, but archaeologists speculate it may have had something to do with their size. The reason I mention them is not just because it's fun to bash SUVs and the fact that they are trucks to avoiding the clean air provisions and the gas mileage provisions, but they're cars because they don't drive in the right lane at 55 like trucks should. But because regardless of your views of that, if you're an analyst, you have to project human behavior. So you have to project how many people are going to be in the world, what are their standards of living, and what technologies are they going to use, because those determine emissions. So you can't even begin to do your crystal balling with the perfect Earth systems models if you don't have some projections of human behavior. In fact, we do scenarios. Not only do you have to predict that, of course, there are those who think they're really good things, so you can bet that anything I like, the Wall Street Journal editorial board, is on the other side. Okay, this is one of my favorites. What was that old Simon and Garfunkel thing? The wisdom of the prophets is written on the subway walls. Well, this is a subway wall in Washington, D.C. about Hummers, right? They do well at the polls. They were melting the polls. And of course, in our free market economy, these items accessible to the poor are subsidized. But anyhow. So there I am, of course, politically correct with our Honda Civic Hybrid that we drove down here in and got twice the mileage for two of us than we would have in an airplane seat. And then there are the good wind power, and I'm not going to make the case that wind power is going to take care of 100%. In fact, I think we'll be lucky if we do much more than 25 because there are a number of impediments, both technological, having to do with boundary layer energy, intermittency. So the key is not what's correct politically, but what can we say reasonable about future scenarios that we then would drive these Earth system models with so that we can give forecasts to people like Terry who's going to tell you what it might mean. So that's why IPCC, the Intergovernmental Panel on Climate Change, had a very large group of about 25 people working for 3 years with multiple rounds of review trying to fashion scenarios. So here's a set. Okay, the year 1000, the year 2100. So this is carbon dioxide concentration in the past. It's based on bubbles and ice cores. So they're direct measurements, but they weren't direct atmospheric measurements. Here's the 30% increase that we've seen since the Industrial Revolution. And here are 6 projections from about 550, something like that, parts per million, up to, I can't even read the number, over 1,000. Now, the pre-industrial is 280. So what we're looking at is, at best, a doubling of CO2, at worst, a tripling. Notice also that the doublings are flat. That means that the system is stabilizing, that is, the economic system is stabilizing, whereas under the assumptions of the worst one, it's still going up in the 21st century. We'll see vastly more increase than we will see just in the next 100 years. Now, these various scenarios have not been assigned probabilities. We have long arguments about them. The top one is called the fossil intensive. That's business as usual, use all the cheapest things, no internalization of externalities, none of that. The lower one Here is what we call A1T, or technology. That's the same world. It's a globalized world, lots of trading, not a lot of effort to bring up the poor, but they come up just on the rising tide of the economy. But there's a lot of money spent, on the order of 1% of GDP, on trying to get high technology. So that's still a CO2 doubling scenario. Okay, now let's translate that into what you care about, which is temperature change, because that's what species feel. They don't feel, well, they do feel CO2, but that's another issue, no time. So here's a 1,000-year record. The thermometer was only invented back around here, so how do we know about this? Well, you look at proxies, tree ring widths, oxygen isotope ratios of coral reefs, borehole temperatures. There's a range of them. And there's a lot of uncertainty from year to year, and this is a 50-year running mean. And then there's the 20th century, the first warming pulse, and then this weird thing that goes up above the noise. So that's part, again, of the reason why people think that this is unusual. But what I'm interested in now is crystal balling. So let's project forward using each of that fan of the 6 scenarios from the IPCC and say, what does it mean for temperature? Well, you notice there are bars on the side. Those bars, each one is color-coded to one of the scenarios, because what it says is that for each scenario there's a range of temperature. Well, where did the range come from? That's another fan of uncertainty. That comes from a geophysical property of our Earth systems models, our somewhat partly cloudy crystal balls for the Earth, and that's what we call climate sensitivity. Climate sensitivity is by how much does the Earth warm up in equilibrium, that means wait a few hundred years for the oceans to catch up, if you doubled CO2. And the number typically used to range from 1.5 to 4.5 degrees, and that's based upon models, not upon direct measurements. So that's the range you get between about 6 degrees C and about 1.5 degrees is the projected range for 2100. Just to give you some perspective, 5 to 6 is the difference between an ice age and an interglacial. This is a dramatically large change. This one is as large or larger than any we've seen in our particular geologic epoch, the last 10,000 years, but certainly would be much more manageable than that. So it really matters from the social point of view whether we're lucky and come out down here or unlucky and come out up here. But we also have some control because these scenarios we could choose. Okay. So let's go re-examine this question of sensitivity, because uncertainties have been brought up, and we certainly have plenty of them in climate as well. So what this is meant to represent is the well-calibrated range of uncertainty. Model 1, Model 2, Model 3, Model 4. So that's the 1.5 to 4.5 degree warming if you doubled CO2. We all know the models leave things out. So if you do a decision analytics survey and you ask scientists, well, knowing what you understand about the system as well as what you can model, what do you think the range is? And Granger Morgan has done this. It turns out to be a substantially larger range than what's modeled. So let's call that the judged range. And if you read the cognitive psychologists like Kahneman and Tversky, they tell us that we experts tend to be overconfident. So I would say that the actual full range is even larger than that. And there's no way to avoid some element of subjectivity, even in something that seems as, quote, objective-oriented as what's the sensitivity of the climate. Okay, so let's apply that. So here is the new way we try to approach this problem. Instead of just giving 2 values, let's take a look at a probability density function, which says here's climate sensitivity and here is a probability. You notice that the bulk of the odds are inside the 1.5 to 4.5 degree range, but they're very long tails. In this particular one from MIT, here's one which I want to spend 2 seconds on from University of Illinois, from Natasha Andronova and Mike Schlesinger. So there's their probability density function. This one they derived empirically. That is, they had a model of how the system works, which is semi-empirical, and then they took a look at all the forcings they could find in the literature, the greenhouse gases that warm, the aerosols that cool, and so forth, the sun, and they then tried to fit the temperature of the last 50 years to get best fits. And when they do that, they get this distribution with this funny long tail. And the reason for the funny long tail is we can't constrain very well the sulfate aerosols. So if there was a lot of cooling due to those aerosols, then the fact that we've only warmed up 0.6 of a degree now may not mean that we can extrapolate that 0.6 for CO2 in the future. That it could be much larger than that because the aerosols were holding it back. And again, I don't have time to explain the details, but that's where these things come from. So now you do a cumulative density function of this, and for those who are not familiar, that's just the area under the curve. And if you look at and it's convenient because you can do percentiles. So what's the 10 percentile climate sensitivity, it's 1.1 degrees. That's below the canonical range. So that means you have a 10% chance it's 1.1 or less. Basically, the problem is not going to be much, if that's true. On the other hand, you have 90% chance it's higher. The 50-50 is at 2 degrees, and the 90 percentile, that means it's 90% likely to be less than 6.8, but it's still 10% possible that it could be greater than 6.8, which in my view would be utterly catastrophic. So people say, well, only 10% chance, and I always like to quip, well, if there were a 10% chance that you had salmonella in the salmon, you're going to eat it. So now we're out of the realm of analysis and back into exactly what I heard people say, where do you put the line in the sand? How do you make decisions about risk methods? Okay, so let's apply this. How much? I don't want to use more than about 20. How close am I? I'm over already? All right. We started 1:30. Okay, I'm about done then. All right, so let's take a look at what this means. So here it is, global warming to 2100 for the A1T. That's the high technology scenario. That's where you basically get off carbon emissions by the end of the century by investing in alternative energy. I drew a line at 3.5 degrees as a very conservative measure of, boy, you don't want to go above there. And it also was the value for a previous report. So the blue is a nasty territory. I in fact think the European Union set 2 degrees as their limit for, quote, dangerous interference. So take a look. If you're at the 10 percentile level, you don't even get over 2. If you're at the 50 percentile, you get to over 2, so the Europeans don't like it, but it gets near 3. And if you're at the 90 percentile level, you're up over 8. So, and that's with the strong investment in emission controlling technology. What happens if you're in the business as usual, use all the coal scenario? Well, then you end up, as you can see, much larger at this end. But there's something very interesting. Take a look here, just at 2040 or 50. About 1 degree, around 2 degrees, around 4.5 degrees. If you look at that so now I put them together. So here's the fossil intensive, use all the coal. Here's the high technology one. For the first 50 years, they look about the same. So people say, well, policy doesn't make any sense. I mean, after all, if they're going to look the same, you're not going to get anything. I heard that today. Policy doesn't matter if we can't prove that it's going to work. Well, they're right if you focus, in climate, if you focus in the first 50 years. The reason for that is that both of them start up at the same rate. But then as we start inventing the new alternatives and they become cheaper, the emissions go way down. So what we do now affects the trajectory of technology, which then affects sustainability over time. So not only do we have to look in the short run, but we've got to have, at least in the climate change, a couple of century perspective, or you're going to miss the sustainability issues. And I think that from what I've heard from Mike Rosenzweig and others is when you take a look at extinction rates, just because you don't see it now or in the next 10 years doesn't mean it isn't a dynamic built into the system that will play out over time. So we have those analogies. Now what Terry's going to do is she's going to talk about what that might mean. I was going to say, we know that the glaciers of the world are going down, and I don't want to convince you that we know that global warming is a fact. The debate is over the extent to which humans have done it. That's the debate, not over whether the earth is warmed. We know that that'll push birds around. Some birds are stranger than other birds. Global warming, I don't know, right? Seems cool down here. Okay, real science now.
Thanks. I appreciate you setting up my talk for me. It may seem like a non sequitur a bit to go from talking about the Endangered Species Act to now talking about global warming. But I think what we need to remember is there are synergistic effects that are going to be going on. And as Dave Wolkov has said, the real trauma to the species thus far has been the modification of habitats. So now we have the modification of habitats, and on top of that, we now have to also put on what's going to happen with global warming. So that's where, I think that's basically why Mike invited us to come and talk to you all, is to say we've got to start thinking about this in the future. But before we think about it in the future, I want to go through some basically about what's gone on in the past so that we know the past will help us understand what's going on in the future. This is just a plot showing you, just trying to convince you that indeed the globe is warming. This is on the y-axis is showing you departure from mean temperature, and you can see that there's an upward trend. this is the same plot that Steve just showed you, that you have an overall downward, actually it looks like it's cooling, and then all of a sudden here we have this incredible upswing, and that's what we're experiencing now. So yes, indeed, the globe is warming. It is a fact. The real question is, are we doing it or not? Now, how does global warming affect species? This is just to remind us how sensitive species actually are in communities. Back in the 1860s, on this axis is time, on this axis is relative abundance. Back in the 1860s, we decided we wanted to get rid of wolves. We did a really good job, but we had, as Bruce Babbitt likes to talk about, we had this funny train wreck. All of a sudden, we had this incredible... I didn't do that. This incredible surprise of the fact that once we got rid of wolves, all of a sudden up popped the coyotes. Then we decided, let's get rid of the coyotes. We pushed the coyotes down. Now what happens? Up pops the red foxes. So there are all these surprises that are going on. There's also been a very nice study that has shown that we've been spending oodles and oodles and oodles of money trying to increase the abundance of dabbling ducks. And a study has shown that if we get rid of the red foxes and actually introduce coyotes or wolves, then we will increase the dabbling ducks, because the red foxes are really good at destroying dabbling duck nests. The point of this, though, is to show how much, how easy it is to shift communities. If you push on one thing, something else is going to happen. So if now what we have is we're pushing on one species or another, with habitat destruction, and then we're also pushing at the same time with global warming, what are the surprises that we're going to see? And that's what I want to go on into now. So what I want to do is I'm going to do two things. First, I'm going to talk about a meta-analysis that we did using data from the literature of what people have found about species in the past. And then the second thing I want to do is talk about possible future changes. So now, what we wanted to do for the meta-analysis is we examined all of the papers in the literature that we could find that looked at species change and changes in temperature. We didn't look at precipitation. I'll go into that later if you want me to. We had to have a change, so we had to have at least 10 years to make sure that we had the change, and then we had to have two different types of studies. The Tier 1 study here are the studies that we included in the Intergovernmental Panel for Climate Change report that came out. And for this, what we did was we said a trait of a species, something like migration change or distribution change. The trait of the species has to show a statistical trend over time, and either the trend is statistically associated with temperature, or that temperature is shown to have a statistical trend over time also. So those are the Tier 1 studies. Then we have the Tier 2 studies, and these studies were added to the research that we published in Nature just recently. And this, we basically threw out the fact that we didn't have to have statistical significance. So we have all of these rules, and we came up with, we looked at over 2,500 studies, that actually is closer to 3,000 studies, on species and climate change. 85 met Tier 1, 58 met Tier 2, so we really pared it down, but we still had several studies that we were looking at. Now, where were the studies? They were all over the globe. They weren't just in one region, so people can't say, well, sure, it's affecting Northern Europe, but it's not affecting other places. This is all over the globe. It's also very different taxa, so it's not just my favorite, being birds. All the taxa are being represented pretty well. And so now what we had was we found that there were about, in all of these studies, we found that there were about 1,800 species. Now, what we wanted to show was how the species are being affected by global warming. Now, I can't tell you how many species are being affected by global warming compared to the overall number of species that there are in the world, because we don't know how many species there are in the world. So that would be a nonsensical type of relationship. But what I can show you is, of the species that are actually changing, how many of those species are changing in the direction we would expect with global warming. So to do that, what I needed to do was get rid of all the species in the studies that were showing no change whatsoever, and that was about 20% of them, and so we threw those out. So now what we did was we had about almost 1,500 species that we were looking at, and we wanted to look at the different types of changes. The changes that we saw had to do with phenological changes. They were arriving earlier in migration, leaving later in the fall migration. Eggs were being laid earlier. Trees were blooming earlier. There were shifts in abundances and ranges. There was a shift poleward in the ranges and also up in elevation. And then there's miscellaneous stuff that you kind of have to have a miscellaneous group here. And that's where you have changes in gene frequencies and things like that. So those are the various changes. And so what we did for the meta-analysis is we did two different types of meta-analyses. The first one is vote counting, and all that is we go through and we looked at all of the species and said, is the change that the species is exhibiting, whether it be phenological, change in the range, change in genetics, is that change in the direction expected if there were global warming, or is it not? And we counted up how many there were and how many there were not, and that's what vote counting is. And then I'll get to the correlation coefficients in a second. So for vote counting, we combined all the changes, and we looked at what was and what wasn't. And of the almost 1,500 species that were changing over time, 20% were changing in the way that we did not expect, but 80% of them were changing in the way that we did expect. So now, if I stood here and I flipped a coin 100 times, and 80 times it came up heads, I think all of us would say, that coin is probably loaded. So what this is doing is saying, basically, that yes, global warming is loading our species to be changing. So now let's look at the correlation coefficients meta-analysis, and for this we wanted to look at phenology. And so we looked at all the spring phenology. So we wanted to see, is our species changing earlier in the springtime? And we looked at the time period from the 1950s onward. We had 61 studies and almost 700 species. And here are on this axis is frequency of species. On the bottom axis is the number of days of change per decade. So what this is showing is that there is one species that is actually doing something earlier by 24 days per decade. So, and this is over the last 50 decades. So that's quite a change that's going on here. We do have some that are coming later, so it's 6 days later instead of 6 days earlier. But we have this nice peak here, and the arrow now is showing you what the average is, and that average is about 5 days of change per decade on the earlier side for the last 50 years, which is non-trivial. What that is telling us is that the globe is warming, and that is causing species to change and to move. So now what I'd like to do, we'll go on. What I want to do now is go to my second point and talk about the possible future changes. And this is what I think needs to be considered when we're talking about the Endangered Species Act. And this is a little bit sobering. So it's following up now on what Steve was talking about. And what we have found, and what we predict to happen more in the future, is that if we have these two species that have overlapping ranges, if one of them, say bird A, is limited by temperature currently, it's going to shift its range north, while bird B, which may be limited by vegetation, which takes longer to shift, or by some kind of prey item, which may take longer to shift, that B is not going to shift as rapidly. So now we have what I like to call a tearing apart of our communities that we have today. So now, is that going to be a problem, or is it going to be fine? The answer to that is yes. We really don't know. It's going to have to be species-specific and look at it on a case-by-case basis in some situations. We're going to have a breakdown of predator-prey relationships. We can have a breakdown of competition relationships, but that may not be dramatic, and it could very well be dramatic. So we need to keep our eye on all of this. Okay, this now is just the same slide that Steve showed you, and you have the 5 different scenarios, which none of you can see. But what I did was I took the lowest of the scenarios, and that was the one where you have shared technology. We don't have the isolationism that we're seeing right now in the Bush administration, but we actually have global exchange of technology. And then I used one of the highest up here, and that is business as usual. That is assuming that we continue on just like we're doing right now. We don't work on the Kyoto Protocol. We just keep going as we're going. So those are the 2 scenarios that I'm looking at, and I am projecting now out into the future what could be going on with species. So we're looking at the fossil intense world and then the technological world. Okay, now to get at this, what I did, I actually did this with my nephew, who is an undergraduate at Carleton. We decided that we wanted to try and figure out what might be going on with some species given those 2 different scenarios. And since my nephew lives in Minneapolis, he decided that we wanted to do a transect, a longitudinal transect that went through his hometown, and so went from the Gulf Coast all the way up as far as we could make it go. And we wanted to see along that transect how birds that we know are limited by temperature in the wintertime, how those species ranges might be shifting, assuming the 2 different scenarios, the fossil intensive and the technology. All right, so now on this axis down here is latitude. So we're going from closer to the poles up to closer to the, closer to the equator up to the poles. And this now is change in temperature. And as you get higher in latitude, the temperature change, the amount that is actually changing, is larger. And we can go into that later if you want to. But this is the overall change. This is for year 2050, so this is just a snapshot. And now we have here that there's a 90% chance that by 2050, if we have a business as usual, fossil intense world, that this is going to be the change in temperature. We have a 50% chance that it's going to be along this line, and we have a 10% chance that it's going to be along this line or higher. Now, as Steve told you, fossil intensive and technology don't change much at 2050. So remember that graph for a minute. Now here is fossil intensive for 2100, and now this is what's quite sobering. We have a 10% chance of, by 2050, at the high latitudes, 55 degrees north, that there's going to be a 5-degree warming. This is the 50% chance, and now this is the 10% chance. So here we have 90% chance, 50% chance, and 10% chance. Now we look at technology. This plot looks basically exactly like the first one that I showed you. There's not really much change because there's not much technology. They assume that there's not much technology that is actually being shared at this time. It's taking about 50 years to ramp up and get the technology going. But now if we look at 2100, it shouldn't be as bad as it was before, and it's not. It is, because I went backwards. Okay, it's not. So now we have the 10%, sorry, I keep saying that backwards, the 90% chance that it is going to be at 55 degrees latitude. It's no longer up at 5, it's dropped down to whatever that is, 2.5. The 50% chance is here, and now the 90%, I keep doing it backwards, the 10% chance has dropped down quite a bit. But regardless, I would suggest that anything that is above about 3.5 to 4 degrees is going to be pretty catastrophic to species. So now, this is a very confusing plot, so let me walk you through it. Here is the transect, and going from the Gulf Coast all the way up now into the Arctic, above the Arctic Circle, which is here. The edge of the U.S. is somewhere around here. There's not an exact fit, but it's close enough. It gives you some idea what's going on. So on this axis is location, degrees of north latitude. On this axis down here are birds, and if you're a bird person, you'll have a really good time trying to figure out what all those little abbreviations are. But each of these is a species of bird. Now, how you read this is the bottom line here, or pick one here, the bottom line here is where the range, the northern range edge is currently. The next bar is showing you that we have a 90% chance of the range going to that location if we have in 2050, whether we have a technologically sharing society or a fossil-intensive society. The next bar up is showing you that you have a 50% chance of having the northern range there, and the next bar is saying that you have a 10% chance of having the species northern range shift by that much. So this is what's going on in, or the projected, of what may be going on in 2050. So there really is, as you can see, there really is a shifting going on, and it is a concern that we need to be thinking about when we're talking about where reserves are going to be placed and what's going on with the Endangered Species Act. Now what I want to do is I want to show you what these data project out for 2100. And this is for the fossil intensive. And I hope you all laugh instead of cry. Okay, here we have, this is where the American goldfinch is currently. In 2100, if we have business as usual, there's a 90% chance that it's going to shift up into Canada, a 50% chance that it's going to shift up above Churchill, and a 10% chance that it's going to shift up above the Arctic Circle. Now, this is all assuming that everything is stable, that the habitats are available, the predators, the prey, everything is available. This is just looking at temperatures. So this is very sobering, at least to me. But remember, this is fossil intensive. So now let's look at what it is if we stop all this isolationism and really get some cooperation going and sharing technologies. That's the plot. So it isn't as bad. The goldfinch now comes right up, not above the Arctic Circle, but it still is pretty high. The question here is what's going on to the species that were up here to begin with? Are they getting pushed off the top of the globe? In my opinion, we literally are standing at the brink of a mass extinction around the world. And it is going to be caused by us, by just one species. And we need to, in the U.S., I think that the Endangered Species Act is the strongest stick or honey or vinegar, whichever way you want to look at it, to actually try and stop some of the extinctions that could be happening in the future with the synergistic effects of habitat destruction and global warming. And now, if you didn't think you were depressed yet, let me go through this one. This one is very sobering, and there aren't any numbers or anything on these axes because it's all a cartoon. That's all it is. It's just a cartoon. On this axis now is magnitude of a response, and on this axis down here is time in years. This first plot, this one here, is showing you what the concentration is of the emission of CO2 into the atmosphere, a greenhouse gas. This right here is assuming that, boom, we are finally able, via Kyoto protocols plus whatever else goes on, what other treaties go on, what other sharing goes on with technology, stopping the isolationism, we can change the emission of CO2 in the atmosphere and actually have it start dropping down, and it will asymptote somewhere down here. It won't ever go to zero, but it will go down. All right, if we have that switching going on, this line here is showing you what the temperature could be in response to what's going on with this CO2 curve. And you can see that it is still continuing to rise and continuing to rise, even though this is dropping down. Eventually, this will come down, but it's not going to come down dramatically. It's going to come down a little bit. The temperature is still going to be high. I forgot a line. This is the CO2 stabilization. This is the emissions. This is what's actually going to be in the atmosphere. And why I say this curve, the temperature curve, was going to drop down is because this one is actually going to be dropping down due to this. So we're going to have a dropping down here. We'll have a temperature dropping down there. But the point is, look at the increase of the temperature, even though we can at some point stop and turn around the amount of CO2 emissions. These two curves, Steve can talk to you about them better than I can, but what they are showing you is, if you look at the solid one, that is how much the sea is going to rise just due to plain, ordinary thermal expansion. Let's forget all melting. All we have is thermal expansion. So even though we have stopped putting CO2 into the atmosphere way back here, this curve is still rising. It's still going up. And then if you add into it, on the dotted line, you add into it melting of the ice caps and glaciers and things like that, man, we're just going hell-bent for high water there. Well, pardon the pun. Anyway, so you really do, we are going to have this increase in sea level that's going to be quite dramatic. And that's of concern because about 35% of the human population lives around the coastline. So now what's going to happen to our estuaries? What's going to happen to our species that now are going to be trapped between the rising ocean and the humans? It's going to be a difficulty. So let me end now with this plot. Steve showed this to you briefly. This is the Baltimore Oriole. This is the plot that Al Gore would carry around in his shirt pocket and would show it every now and then. This is a mathematical model of the present day distribution for the Baltimore Oriole, and it's based on a climate envelope. Now, if you assume that there's going to be 2 times CO2, and we're using the Canadian climate model, and assuming that model has 2 times CO2, and assuming that all of the weather parameters, climate parameters, are determined by that model, the actual range now of the Baltimore Oriole is going to be in this location here. And so Vice President Gore got a real kick out of this, because we better do something quick, because there aren't going to be any more Baltimore Orioles in Baltimore. Thanks.